We are now at a stage where we will need a few more ingredients only before we can start applying all that we have learned to physical problems. One of the final pieces that we will need is the ability to choose a nice basis. Let me explain what I mean here. As we have been saying over and over again, there are many situations where representations that occur naturally in a physical system are reducible. That is, you should be able to find a change of basis in which the representation matrices will become block diagonal, or in more geometric language, the actual vector space on which the group is acting consists of many subspaces which are individually invariant under the action of all the elements of the group. And it is these invariant subspaces which carry a lot of information about the physical implications of the symmetries that the system has. So it would be wonderful if we could actually have a prescription for finding out a basis in which our representation matrices become block diagonal, which of course means that we are trying to find vectors which essentially form invariant subspaces under the action of the group elements. What we are going to study next is one systematic way of finding out such basis vectors. This is by means of what are called projection operators. The idea is that we will start from an arbitrary vector in our vector space and then apply a projection operator which will give you a vector which is in some invariant subspace only. How do we find out such projection operators? That is our next topic. In order to develop the basic theory of these projection operators, let us start with a vector space V that carries a reducible representation of our group, capital G. Now, because V carries a reducible representation, it can be written down as a direct sum of irreducible invariant subspaces, that is, subspaces each of which are invariant under the action of all the elements of the group, capital G, and each of these subspaces cannot be broken down into further subspaces which are themselves invariant. This means, of course, that every vector small v of capital V can be written as a sum of many vectors, each belonging to one of these irreducible invariant subspaces. On the other hand, a vector in an irreducible invariant subspace can of course be expanded in terms of a set of basis vectors which belong to that particular irreducible invariant subspace. If you combine these two statements together, it immediately implies that a basis for the vector space capital V can be built up by putting together the basis vectors for each of these individual invariant subspaces. Now, a given irreducible invariant subspace will transform under the action of the group G like a particular irreducible representation. Say, a particular subspace may transform like the representation labeled by beta. What we will do is write the basis vectors corresponding to this subspace with a superfix beta to indicate that. So what we would have is, of course, vectors like v beta 1, v beta 2 all the way up to v beta d beta. However, we must account also for the fact that a particular irreducible representation may occur multiple times in a particular representation. What that means is that other than v beta 1, v beta 2, v beta d beta, there may be another set of vectors, maybe v prime beta 1, v prime beta 2, v prime beta d beta, which also transform among themselves according to the irreducible representation d beta under the action of the group. Now, in order to keep track of all these, what we do is we add a second index m to the superfix here. So, what we write here is that a basis vector will be of the form v beta mk, where k can run over 1 to d beta. Beta, of course, labels a particular irrep, and m runs over 1, 2, 3 up to m beta, where m beta is the number of times this particular irreducible representation beta occurs in my representation. So finally, any vector v can be expanded, of course, in terms of the basis vectors in capital V, and such a vector can always be represented in this following form, V beta mk, C beta mk, summed over k going from 1 to d beta. This, of course, for a particular beta nm, this gives you the piece of V which is within a particular invariant subspace. But now you have to sum over all the m's possible, 1, 2, all the way up to m beta. And of course, you have to sum over all possible irreps that the group may have. A sum from beta equal to 1 to beta equal to number of irreps. And the number of irreps, as you all know, is equal to the number of classes, nc. If you look at the sum closely, you will find that each one of the pieces of the sum make perfect sense, although it may look a bit intimidating in one go. Our job would be to try to take out of small v a vector which belongs to only one irreducible invariant subspace. So basically extracting a piece of the vector v which sits in a particular invariant subspace. And that is what we are going to do now. We know how each and every one of these v beta mk's respond to the action of the group elements. This tells us that we can also figure out how any group element G acts on V. Of course, a group element G acts on V via a linear transformation, L of G acting on V. And when L of G acts on V, L of G being a linear operator goes right into the sum, goes past the coefficient C beta mk and goes and acts on V beta mk. But now, notice V beta mk is nothing but the kth basis vector in the mth copy of the representation labeled by beta. So this is going to give me L equal to 1 to d beta lkg v beta ml. All we are saying is that the beta representation is an invariant one. So when you applied Lg on a vector in that representation, you are only going to get a linear combination of all the basis vectors belonging to that particular representation. And only that particular representation. And the coefficients, of course, are our familiar coefficients for d beta lkg of the beta irreducible matrix representation. Now, this is straightforward application of Lg on V, but now we are in a position to exploit the great orthogonality theorem to our advantage. I have said earlier that almost all things that we can figure out from the great orthogonality theorem can be figured out with less effort using its simpler cousin, the character orthogonality theorem. However, for the projection operators, you can't really work with the character orthogonality theorem directly. You have to actually use the full power of the great orthogonality theorem here. In order to use that, what we are going to do is we are going to multiply both sides of the equation by the numbers d alpha ij g inverse, where alpha is label of some irrep, and then you are going to sum up over all group elements. So this is being done on both sides, and the new things that we have put in, I have indicated in blue here. But now notice that the sum over group on the right is only done over d alpha ij g inverse d beta ikg. The rest, of course, are independent of the particular group element you have chosen. Now, when you carry out this sum, the result is straightforward. This is exactly what our great orthogonality theorem in its original version gave us. And the result is going to be mod g by d alpha, delta alpha beta. The two irreps must be the same to get a non-zero value. Delta lj, delta ik. The rest of the terms, of course, stay just as it is. Now that the great orthogonality theorem has given you so many delta symbols, it is easy to carry out the sums explicitly, and very trivially the sum just works out to be m equal to 1 to m alpha mod g by d alpha ci alpha m vj alpha m. Note that while we have started with a vector small v, which is an arbitrary vector in our vector space, and so has components in each and every irreducible invariant subspace, the final result here is a vector which has only components in those subspaces which carry the irrep labeled alpha. You still have a sum over m going from 1 to m alpha, and that means that if you have several occurrences of the same irreducible representation in your vector space, then this operator d alpha ij g inverse Lg summed over all g acting on V will not be able to pick out a particular basis vector, but it will pick out all the jth basis vectors in all copies of the alpha irreps. From this, what we can do is we can define an operator P alpha ij as this operator in blue sum over all group elements of d alpha ij for G inverse times Lg. These are our projection operators. Why are they called projection operators? Note that when they act on a vector V, which could be any arbitrary vector in the vector space capital V, the result is always in the direction of the jth basis vector of an invariant subspace, which transforms under the action of the group like the irreducible representation labeled by alpha. So what goes in as an ingredient for building up these projection operators? What you need here are the operators which act on the vectors in your original vector space capital V, one for each group element. That is, you need to know capital L of G for this. But what you are really doing is that you are weighting each and every group element by d alpha ij G inverse. Notice that in order to calculate these weighting factors, what you need to know are the matrices corresponding to the different irreducible representations. So this is one place where you do need to go beyond just the characters. The character for a particular group element, remember, is just the trace of the representative matrix. Characters are enough for many calculations. However, for this kind of calculation where you want to build up a projection operator, you actually have to go beyond the character and you have to go and use the actual matrix elements. Now in the special case where the irreducible representations that you are using happen to be unitary, this can also be written in this particular form. You can replace the d alpha ij of G inverse in the formula for the projection operator by d alpha jig's conjugate. This simply follows from the fact that all the matrices of an unitary representation are also unitary matrices. That is, the inverses are the same as the adjoints. Now, what these operators do, as I have said, is project onto an invariant subspace V alpha. To be precise, the projection is not really to V alpha, it is actually a projection to the direct sum space of V alpha M. That is, all the invariant subspaces which transform according to the same irreducible representation are clubbed together into a direct sum, and what this projection operator does, when it acts on an arbitrary vector V, produces a vector which is in this direct sum vector space. Now, for each alpha, I and j can take d alpha distinct values, where d alpha of course is the dimensionality of the alpha's representation. That means for each irrep you have d alpha square projection operators. That of course is a problem of plenty, because for a given irrep you actually have only d alpha basis vectors to project to. But here you have d alpha square number of operators which does the projecting. For many purposes it is enough not to use this many projection operators. Rather than allow I and j indices to take arbitrary values, you choose both of them to be equal. So these are called the diagonal projection operators. Here the weighting factors d alpha I g inverse are the diagonal elements of the d alpha irrep matrices. And again, for the unitary case, this simply becomes d alpha I star g Lg. And what happens when p alpha I, this particular projection operator, acts on V? That's pretty straightforward. What you are going to get is mod g by d alpha once again times ci alpha m v alpha m. Notice that in the general case you do get a vector in the direction of vj alpha, but the weighting factor is not the original coefficient cj. The weighting factor is actually ci. Here, because you are using diagonal matrix elements only, what you end up with is a vector in the direction of vi multiplied by the original coefficient ci alpha m with an additional factor of mod g by d alpha thrown in. Now I admit that all this plethora of indices and all this rather complicated looking expressions may make this seem a lot more difficult than it really is. To see how easy it is to use these projection operators in actual practice, let us fall back on our old friend, the group S3, and let us talk of a reducible representation of the group that we had already met before. This is our 3D representation of S3 provided by a space of homogeneous quadratic functions on R2. We had already seen that this is reducible. It's a direct sum of two representations, A1, which is the identity representation, and the two-dimensional representation that we call B. And here is a table which lists what happens to each of the basis vectors that we used, F1, F2, and F3, under the action of LE, LA, LB, LC, LD, LF. If you have forgotten how this works, I will urge you to take a look at an earlier video where we explained this thing out in full. Just to remind you, F1 is basically a function which maps a vector with components x, y into x square plus y square. F2 mapped the same vector into x square minus y square, and F3 mapped this vector into xy, the product. And when we applied each of the group elements E, A, B, C, D, F on the underlying vector spaces, we could use that action to see how x and y change and use that to figure out how F1, F2, F3 will change to give you new functions. And this table essentially tells you what happens to each of the basis vectors F1, F2, F3 in this three-dimensional vector space of homogeneous quadratic functions under the action of each and every one of the group elements. Using these actions, LE acting on F1 is F1, LB acting on F1 is 1/4 F1 plus 3/4 F2 plus root 3 by 2 F3 and so on, and using the irreducible representation matrix elements for the two irreps A1 and B, we can write down all the projection operators. As we have already said, we can just use the diagonal projection operators, and that's going to be enough for the purpose of finding out combinations of F1, F2 and F3 which form invariant subspaces or basis vectors for invariant subspaces. So first, let us take a look at the invariant subspace labeled by A1, which is the subspace which carries the identity representation. And this is a one-dimensional subspace. The indices I and j can only take the value 1. So basically we are talking about A1, 1, 1, which is just nothing but the element of the particular representation, because this is a 1 by 1 representation. And because we are talking about the identity representation, each one of the group elements is essentially represented by the number 1. So what we have to do to find the projection operator corresponding to this particular irrep and corresponding to this particular pair of indices, although that's the only possible combination here, is to weight the action of LE, LA, LB, LC, LD, LF by these numbers 1 each and apply the combination on the basis vectors F1, F2, F3. So basically what you are going to do is 1 times LE plus 1 times LA plus 1 times LB plus 1 times LC plus 1 times LD plus 1 times LF acting on, let's say, F1. And we know what that's going to give you. It's going to give you the sum of all these vectors in this column. And that sum, if you just carry it out carefully, would simply work out to be 3 times F1 plus F2. Here, also you get 3 times F1 plus F2 from acting on F2. Acting on F3, it gives you 0. So what this tells you, essentially, is that the original basis vectors F1, F2, F3 were not basis vectors for the invariant subspaces. We knew that already because our matrices did not have the block diagonal structure at all. It tells us that both the vector F1 and the vector F2 has a piece in the direction of this particular invariant subspace, the subspace which carries the representation A1, and the basis vectors for that, which you get by applying this P A1 1 1 on F1, F2, F3, turn out to be 3F1 plus F2. Of course, you could drop the 3 and just take F1 plus F2 as a basis vector. Notice that both F1 and F2 under the action of PA1 1 1 gives you the same result, 3F1 plus F2, telling you that F1 plus F2 is a basis vector for this invariant subspace which carries the irrep A1. F3 on the other hand vanishes under the action of PA111. What that really tells you is simply the fact that F3 has no component in the direction of that particular invariant subspace. So the upshot of all this is we have managed to find out one basis vector which will allow us to get an invariant subspace. Of course, this particular representation being one dimensional, you only expect one basis vector for that. F1 plus F2 is a basis vector which is going to carry this particular trivial invariant representation. We already knew that because we had already figured out earlier that if you look at F1 plus F2, which is the function which maps x comma y into x square plus y square, that is a function which will not change under the action of any one of these group operations because these operations are just reflections or rotations and none of these operations changes this value of x square plus y square. So one basis vector has been found out this way. We need two more to complete the full set of basis vectors which are going to be useful here. And for that, let us go on and take a look at the A211. A2 is our other one-dimensional representation which has the characters or the matrix elements. Here actually we need the matrix elements, but for one-dimensional representations, characters and matrix elements are one and the same. And these characters are 1, minus 1, minus 1, minus 1, 1 and 1 respectively. Now even before we start building up PA211 and applying it on F1, F2, F3, let me point out that I already know what will happen if I do that. Since our original representation, the reducible three-dimensional representation that we had, was a direct sum of A1 and a 2D irrep B, there was no A2 at all in this representation. What that means is none of these basis vectors F1, F2, F3 will have a projection in the direction of an invariant subspace carrying A2. And that is borne out by a simple calculation. If you carried out LE minus LA minus LB minus LC plus LD plus LF on each one of F1, F2 and F3, what that would mean, for example, is for F1 you would take the first column and then form F1 minus F1 minus 1/4 F1 plus 3/4 F2 plus root 3 by 2 F3 minus the next vector plus the vector after that plus the vector after that. The result, as you can easily verify, is going to be 0, and it's going to be 0 for each one of them. Not really a surprise. We could have actually avoided this calculation altogether because we knew that our irrep did not contain any A2 in it. So the projection in the direction of A2 for any of the basis vectors is bound to be 0. Let's look at dB. And now dB, of course, is a two-dimensional representation. And even if you are sticking to just the diagonal projection operators, I now have two distinct possibilities, PB11 and PB22. And for this, what we need is not just the action of the operators LE, LA, LB, LC, LD, LF. We also need the matrices which form the irreps. In particular, we need the diagonal elements of the matrices only. And we have already worked this out earlier. The diagonal elements are easy to read off from the irreps that we had found earlier. And they are going to be just 1, minus 1, half, half, minus half and minus half. Well, if you use these weighting factors on LE, LA, LB, etc. and combine them together to form this PB11 and apply that on F1, F2, F3, it should be pretty easy for you to convince yourselves that now the results will be F1 will vanish under the action of PB11, so will F2, that will also vanish. F3 will, on the other hand, give you thrice F3. So what this tells me is F3 is actually already a basis vector for an invariant subspace. So we have two basis vectors now, F1 plus F2 and F3. We need one more. And for that, what we need to do is apply PB22. So for PB22, of course, what we need are the components dB22 for the irreducible representation matrices, and use the weighting formula and just calculate now. And what you are going to get is F1 and F2 are both going to give you F1 minus F2 as the basis of course multiplied by different factors, 3 by 2 and minus 3 by 2. But that doesn't really matter. What does matter is that at the end of the day, we now have 3 new basis vectors. F1 plus F2, which carries A1, and F1 minus F2 and F3, which together form a basis for the irreducible representation, which is labeled by B. So what this has done for us is that it has told us what particular combinations of F1, F2, F3 to use so that the invariant subspaces can be seen clearly, and as a result, the corresponding matrix representations will have the standard block diagonal structure. Now this is going to be very, very important because these invariant subspaces usually have physical significance when you are applying group theory to physical problems. So this projection operator approach for finding out basis vectors is really going to be very, very useful. We next turn to an extremely important result which has immense physical ramifications. This concerns matrix elements of linear operators or inner products of the form inner product of V with MW, where M is an operator acting on a vector W and you have taken the inner product of another vector V with it. Of special interest to us, especially in physical applications, are the case of operators M which commute with each and every LG for a symmetry group G belonging to capital G. So, M commutes with every operator in an representation of a group capital G. Just to point out why this is of such importance, if you have a Hamiltonian, for example, of a quantum system, it commutes with each and every LG when G belongs to the symmetry group of the system. This has immediate impact on what kind of matrix elements an operator like the Hamiltonian can have. Which matrix elements of the Hamiltonian are non-zero, and even among the non-zero elements, what kind of connections exist. This result takes a particularly simple form when the vectors V and W which go in the definition of this matrix element happen to be parts of the basis of invariant subspaces which are irreducible under the action of the group elements. If we form the matrix element of an operator M which commutes with all of LGs for every G, between vectors V alpha I and W beta J, then what we get is the following. Firstly, V alpha I and W beta J are not arbitrary vectors. V alpha I is an ith basis vector which forms part of a basis set which spans an invariant irreducible subspace of the vector space capital V. So this is the ith basis vector in an invariant subspace which carries a particular representation labeled by alpha. Similarly, Wj beta is a jth basis vector in a space which carries a representation which is labeled by beta. When you calculate this, the result is that this matrix element vanishes if alpha is not equal to beta. So if Vi alpha and Wj beta are basis vectors or form part of basis vectors for inequivalent irreducible representations, then the matrix element vanishes. Even if alpha is equal to beta, that is, we are talking about the same representation, does not have to be the same invariant subspace, same representation. That is, you may have multiple copies of the same representation which go into the direct sum which forms your vector space. If that happens, even then, what you must ensure is that both the vectors which go in Vi and Wj, they both transform in exactly the same way, that is, like the ith basis vector in both cases. Only then will you get a non-zero value, otherwise the delta ij on the right hand side of this expression will make the thing vanish. If both alpha is equal to beta and I is equal to j, that is, we are really forming matrix element of the form V alpha I, W alpha I of M, then we have a number which we have written with a boldface M with V and W as indices. The V and W as indices indicate the fact that the matrix might very well depend on the vectors V and W involved. However, Notice that there is no I index here. That means for each and every value of I, as long as j matches I, you get the same result. Now all of this put together form what is called the Wigner Eckart theorem, which is a generalization of the special case that you have learned about in quantum mechanics when you talked about rotational symmetry and behavior of rotationally symmetric Hamiltonians. Now let me put in one word of clarification here. You might say that if alpha is equal to beta and I equal to j, then why can't we use just the same vector symbol v for both? The answer here is that v and w could still be different because you may have multiple copies of the same irrep occurring in the reduction. So v alpha I may be one basis vector for one copy and w alpha I may be another basis vector, a different one, for a different copy. But as long as alpha is the same, that is, as long as the basis vectors mix in the same way among each other under the action of the group elements, and as long as you're talking about the same corresponding basis vector in both cases, you are going to get a non-zero value. We will give a detailed example in a while, which will help you to understand exactly what is going on here. But before we go there, let us take a look at the proof of this particular theorem. Before we proceed with the proof, let me issue a caveat. This particular simple form of the Wigner Eckart theorem follows only if you are using a basis for which the representation that we get is a unitary representation. Now that is not a huge restriction simply because, as we had figured out earlier, for a finite group, every representation is equivalent to a unitary representation. So all you have to do is find a proper basis. Even if you were not using unitary representations, you would get a similar result, but the exact form of the result would be a bit more complicated. So we will stick to unitary representation for the time being, and we are going to prove this particular version of the Wigner Eckart theorem. So the proof of the Wigner Eckart theorem starts obviously from the fact that M is an operator which commutes with each and every L of G for all G. So MLG is equal to LGM, and what we do is we take the matrix element of these two operators MLG and LGM, which are equal to each other, with respect to the vectors V alpha I and W beta j. Now if you look at the inner product on the right, using the definition of the adjoint of an operator, it's easy to see that you can rewrite this expression as LG dagger V alpha I MWJ beta. And then all you really need to do is realize that LG dagger is the same as L of G inverse. This is where the fact that we are using a unitary representation comes in. So now the next step is pretty straightforward. We know that WJ beta and VI alpha span or form parts of a basis which spans irreducible invariant subspaces which transform according to the matrices d alpha and d beta respectively. So what you end up with is this result. On the left hand side, LG acting on WJ beta has given me a combination of the basis vectors which span the betath irrep, that is dkj beta g wk beta summed up over all k running from 1 to d beta. On the right hand side, on the other hand, LG inverse VI alpha becomes a linear combination of all the vectors VL alpha, L running from 1 to D alpha, which span the alpha-th invariant subspace. And here the coefficients, of course, are going to be DLI alpha of G inverse. Now, using the fact that we are dealing with unitary representations, DLI alpha G inverse is also the same as DIL alpha G's conjugate. Then, using the linearity of the inner product in the second factor and its antilinearity on the first factor, what we are going to get is simply this. dkj beta g is going to come out of the inner product, and so what you end up on the left hand side of this equation is the inner product between Vi alpha and MWK beta multiplied by dkjg beta summed up over all k. On the right hand side, you have a sum up over all L running from 1 to d alpha of d alpha ILG times the matrix element between VL alpha and Wj beta of this operator M. At this stage, we have elements for the representation matrix for G on both sides of the equation. We will simplify things a bit by getting rid of them from one of the sides. And for that, all you have to do is multiply both sides by d beta Jm of G inverse, the term which has been written in red, as well as sum up over the free index J on both sides. Now the summation on the left over J is very, very simple. It's really nothing but d beta Km of the element G inverse. It's just simple matrix multiplication and the fact that these are representations, so they form a homomorphism. Since G inverse is the identity, what we are looking at is the kmth element of the identity matrix, which is simply delta Km. And now this makes the sum over K trivial, and you're going to end up with K being replaced by small m on the left hand side. So left hand side simply becomes Vi alpha MWM beta, this particular matrix element, that is equal to this rather complicated looking term on the right hand side. But if you take a look at the combination of matrix elements d beta Jm G inverse d alpha ILG on the right hand side, it is absolutely crying out for a use of the great orthogonality theorem. All you have to do is sum up over all group elements small g. So what we do is we sum up both sides over all group elements mod g. The left hand side was completely independent of small g anyway. So when you sum it up over all group elements, all you get is whatever you had earlier times the number of terms in the sum, which is simply mod g. So that's what you have on the left. On the right, on the other hand, you have a sum which has been indicated in red over here, and that sum obviously can be simplified by using the great orthogonality theorem. It is simply mod g by d alpha delta beta delta Im delta JL. So now you have a sum over L and J, and you have delta symbols involving both of them. Now, because of the presence of the delta symbol delta JL, the sum over J on the right hand side is absolutely trivial. All that you have to do here is replace all the other occurrences of the index J by L. You are still left with the sum over L, but most of the factors like mod G by d alpha beta delta Im can move out of that sum because they are all independent of the summation index L. In addition, because of the presence of delta alpha beta on the right hand side, this expression is not zero only when beta is the same as alpha. So we can easily replace the beta in the W beta J by alpha. And after cancellation of the order of the group on both sides, we get this final expression. Vi alpha comma MW beta J is equal to delta alpha beta delta Im times this expression in red, which is 1 by d alpha sum over all L from 1 to d alpha of the matrix elements VL alpha MWL alpha. Notice that because we are using the same index L for both V and W here in this matrix element, we have something like a diagonal matrix element here. Now I am using the diagonal with air quotes, which you unfortunately cannot see. It would really have been a diagonal matrix element if we were talking about the same copy of the irreducible representation. That is, if you were within the same invariant subspace. However, you could be talking about two different invariant subspaces of your reducible space, which carry the same irreducible representation alpha, which means they transform in the same way under the group operators. So this is really not always a diagonal element, so to speak. But continuing with the language of diagonal elements, this is sort of like a trace. And the division by d alpha sort of averages out all the diagonal elements. Note that because of the delta alpha beta delta am present in the formula, all the terms in the sum are really equal. So when you sum them up and divide by d alpha, what you are really going to get is the value of any one of the so-called diagonal elements. And that is what we are calling the boldface MVW. This is the so-called reduced matrix element. So what this is really telling you is that you can relate every matrix element when you are taking them between the basis vectors which form spanning sets for the invariant irreducible subspaces to just a bunch of simple numbers MVW, and most of the matrix elements are 0 anyway because of the presence of the delta alpha beta and delta Im. At this stage, I have a confession to make. I have been calling this the Wigner Eckart theorem. But frankly, this is really a special case of the general Wigner Eckart theorem, used specifically for those operators which commute with every one of the group elements. A more general version of the Wigner Eckart theorem will be introduced if we need them later for a physical application, but this in itself is the single most important version of the theorem, and that is the one we are going to use most of the time. Indeed, this theorem is so important that we should spend some time in looking at its consequences in some detail. Now, one of the easiest things that you would spot here is that if your original representation was actually an irreducible representation, then you can have only one value for the index representing which irrep you are talking about, that is alpha must be equal to beta. And not only that, since there is only one copy of that irrep here, the Vi must be the same as Wi. And in this case, the matrix element can simply be seen to be delta Ij times a number m. Delta alpha beta, of course, is 1 because beta has to be the same as alpha in this case. So, what we really have is, in this particular scenario, the matrix for M is really a multiple of the identity, delta Ij, just the number M times the identity matrix. Now, this should not come as a surprise because this is nothing but simply Schur's second lemma. In this case, M would be a matrix or an operator which commutes with each and every one of the irreducible representation matrices or irreducible representation operators, and Schur's second lemma would tell you that this would definitely lead to M being a multiple of the identity. So this one was. Now notice that this actually tells you that all the eigenvalues of M are one and the same. So if you find one eigenvalue, which you can find out just by finding out one diagonal element, you have got all its eigenvalues. Since eigenvalues of a matrix, which could be something like the Hamiltonian, say, is very, very important, this actually shows you how useful this result can be. Of course, for this particular case, you did not really need to look at the full Wigner Eckart theorem. The Schur's second lemma would have done the trick for you. However, even for a reducible representation, this theorem has a lot to say about the eigenvalues of an operator which commutes with each and every one of the LGs. And that is why this is so useful. To explore this with a concrete example, let us take a look at a 8-dimensional reducible representation which has the reduction given by A1 direct sum A2 direct sum 3 times E. So, if you want to be very definite, you can think of this as an example of an 8-dimensional representation of our friend S3, but you don't really have to be specific about the particular group here. All we are claiming is that the group that we are looking at has at least two one-dimensional irreps, namely the A1 and A2, and at least one two-dimensional irrep. It could have other irreps as well. Since S3 does have two one-dimensional irreps and one two-dimensional irrep, it definitely fits the bill. But the particular representation I'm looking at has three copies of this two-dimensional irrep E. So if you manage to choose your basis properly, you will end up with a matrix for each and every one of the DGs which look like this. Each and every one of the group elements will have corresponding matrices, 8 by 8 matrices, which for this very special choice of basis will take this particular form. It will have two one-dimensional irreps sitting on the top two corners. Those are the red and the pinkish blob that I've drawn there. Then there are these three copies of the irreducible representation labeled by E, a two-dimensional irrep. So each and every one of the DGs will have three 2 by 2 blocks on the diagonal. Let me warn you once again, this is not the form in which an 8 by 8 representation matrix will naturally come, always. This is the form you will get if you manage to choose the right basis. Of course, as we have already seen earlier in this lecture, choosing the right basis is not really a matter of luck. You can use the projection operators that we talked about to find a proper choice of basis. But once you do that, each and every one of the matrices corresponding to the group elements will come to the same block diagonal form. The only thing that will differ from element to element, of course, are what numbers are sitting there in these colored blocks. For each and every one of the matrices, the blocks which do not have a circle in it are all zeros. What we are trying to explore here is the following. If we have an operator which commutes with each and every one of the representation operators, LGs, or a matrix M which commutes with each and every one of the DGs for all the small g's in capital G, exactly what structure does this particular matrix have once you have chosen a basis which manages to cast all the DGs in this block diagonal form? When asked this question, very often students come up with the answer that the M will have exactly the same block diagonal structure as the DGs. The actual answer is a bit more complicated, as we are illustrating with this picture on the right. So a general operator M will have a matrix, an 8 by 8 matrix in this case, which will always take this particular form, where the non-zero elements are once again shown by colored circles. There's a bit more than that here. The color coding also tells you which elements are equal and which elements are not equal. So as you can see, the top corner will have a non-zero element in general, and that is on its own. Everything else in that row and that column is 0, and which immediately tells me that the corresponding basis vector is going to be an eigenvector, and the eigenvalue is going to be given by whatever the top left corner element is. The same goes for the next element down the diagonal, which also is sitting on its own. These are the cases which correspond to the two 1D irreps which occur only once. To understand the distribution of the other non-zero elements, as well as the relationship between their values, let us try to look at this more closely by focusing on the particular basis vectors involved. So I have drawn this picture once again here and have mentioned the basis vectors. S and T are basis vectors which span one-dimensional invariants of spaces corresponding to the top 1 by 1 block and the next 1 by 1 block that our D of G's all had. U1, U2 are basis vectors which span the first invariance of space which transforms according to the representation E. V1, V2 give you another invariance of space which also carries the same representation E. So does W1, W2. So what we have done here is I have labeled the rows and columns of the matrix by the corresponding basis vectors. Now let us take a deeper look at what non-zero elements we have. First of all, let's take a look at this element and this element. These are basically U1 MU1 and U2 MU2, these two matrix elements. And according to the Wigner Eckart theorem, they are both going to be equal to each other. So that is why they have been colored the same way in both. Going down the line, this one is V1 MV1 and this one is V2 MV2. Once again, if you look at the Wigner Eckart theorem, it says that these two will have exactly the same value. So will these two. But because the vectors U, V and W are different sets, the value here and the value here and the value here may very well differ. But you have two pairs of equal values, two pairs of equal values here, two pairs of equal values here. But these are not the only non-zero possibilities. Now the relationship between these diagonal matrix elements is sort of pretty easy to understand, and intuitively we would have thought that that is definitely what you are going to have, because these two form one invariant subspace under all the group operations, and since my M commutes with all the group operations, you would expect these to be the same, and so on. But this one takes a bit more thought. This node is V1 MU1. Firstly, let us understand why this is not zero, or not necessarily zero. Notice that our Wigner Eckart theorem tells you that you are going to get a zero matrix element if the irreps differ, or if the labels of the basis vector within the irrep differs. Now V1 and U1 are different functions. They span different invariant subspaces. However, they form bases of two different invariant subspaces which carry the same irrep, which means under the action of each and every one of the group elements, U1 transforms exactly the same way as V1. And that is what ensures that this particular matrix element does not vanish. Not only does it not vanish, Wigner Eckart theorem also tells you that V2 MU2 will also not vanish and be equal to it. This is the reduced matrix element MVW. These two matrix elements up here are basically complex conjugates of these two, because this one is of course U1 MV1 and this one is U2 MV2. So if you are using a Hermitian operator, which you would usually be using, these two will be complex conjugates of these two. So I've shown them essentially with the same color just to show that they're related in value. Similarly, this one, which is a matrix element between W1 and U1, will be non-zero, but will have the same value as the matrix element between W2 and U2. Similarly, U2 and W2, U1 and W1. All these will have the same value, possibly non-zero value. Once again, because all these are between matrix elements, or all these are matrix elements between different basis vectors perhaps, but the basis vectors transform in exactly the same way because they correspond to the same irrep, and not only that, they're in the same position in the ordered basis for the given irreps. Going along the same lines, W1 MV1 and W2 MV2 may be non-zero and would be equal to each other. Similarly, V1 MW1 and V2 MW2 would also be the same and complex conjugate to the last two. Now let me stress one thing. The values of these non-zero elements would be guided by the reduced matrix elements that you have. Now it might so happen that the reduced matrix element is zero for some other reason. So when I say that these are the non-zero elements, what I really mean is that these are the only elements in the matrix which can be non-zero. All the others have to be zero. If on the other hand, for some reason, V1 MU1 vanishes, then V2 MU2, U1 MV1, U2 MV2 would all have to vanish together. So the fact that U1, U2, V1, V2 and W1, W2 transform in exactly the same way under the action of all the group elements imposes a lot of structure on the possible non-zero elements of a matrix M, which commutes with each and every one of the group representation matrices. But you can also go further than this. Right now, we have labeled the rows and columns by using the standard choice of the basis vectors, S and T for the one-dimensional EDEPs, U1, U2 for the first two-dimensional invariant EDEP, V1, V2 for the second one, W1, W2 for the third one. But the fact that you have these connections between the non-zero matrix elements of M makes it easy to understand that there will be some additional advantage to be obtained if you were to rewrite or reorder the basis vectors. In fact, if I now reorder the basis vectors such that all the first vector in the basis come together, that is U1, V1, W1 come in that order, and U2, V2, W2 come in next. So this is just a change of basis simply because we have rearranged the basis vectors. What happens is something rather striking. Now you have two 3x3 non-zero blocks along the diagonal. And not only that, it should be very easy to convince yourselves that these two 3x3 blocks are exactly the same matrix, have exactly the same matrix elements. So, right now, what this tells us is something like this. If you want to find out the eigenvalues of M, you can of course find the eigenvalues of M prime equally well. It's just a change of basis that has happened. That doesn't change eigenvalues. The top two diagonal elements are automatically eigenvalues. We already knew that. So all you have to do is find out the diagonal elements and you're done. Now you come to the 3x3 matrix which you get when you take the basis vectors U1, V1, W1. If you want to diagonalize this, of course you have to solve the eigenvalue equation for a 3x3 matrix. But that, of course, is much easier than solving an eigenvalue equation for the original 8x8 matrix. So we have a comparatively easier job at hand. And once we find the eigenvalues and eigenvectors of this 3x3 matrix block, the eigenvalues simply give me the eigenvalues of M prime and hence of M. And the eigenvectors for this 3x3 matrix will tell us exactly how to combine U1, V1 and W1 to get eigenvectors for M prime. But note that is all you really need to do, because once you've calculated the eigenvalues and eigenvectors for one 3x3 matrix, the other 3x3 matrix does not need further calculation. It is an identical 3x3 matrix, and as a result, you are going to get the same eigenvalues and the same eigenvector combinations. So whatever combination of U1, V1, W1 gives you an eigenvector for M prime, the same combination of U2, V2, W2 will also give you an eigenvector for M prime. So you don't really have to do the calculation for the two 3x3 blocks separately. Diagonalizing one 3x3 matrix is all you really need to do in this case. So to summarize, you started out trying to diagonalize an 8x8 matrix. Now, if you choose an arbitrary basis set, that 8x8 matrix, despite commuting with all the DGs, could have a very non-trivial structure. All the 64 elements might very well have been non-zero. What Wigner Eckart theorem tells us is that once you choose a basis which block diagonalizes all the D of G's together, the matrix for M will automatically have a very structured form. And not only that, if you then rearrange your basis vectors just by reordering them, you can find a much simpler structure for the corresponding matrix. And note that because you had 3 copies of two-dimensional EDEPs, you essentially end up with 2 3x3 matrices to handle. 3 copies leads to 3x3 matrices, and because the EDEPs are two-dimensional, this whole thing is repeated twice. So the whole problem boils down to finding out 2 diagonal elements for the 2 one-dimensional EDEPs and solving one 3x3 matrix eigenvalue problem, and that will be all that you will need to figure out the entire solution or entire spectrum for this 8x8 matrix M. You would definitely agree that this is a huge simplification compared to just finding out the eigenvalues and eigenvectors of an arbitrary 8x8 matrix. This should convince you of the power of the Wigner Eckart theorem, and this is essentially why using group theory simplifies a lot of physical problems. In the next lecture, what we will do is we will make use of all that we have learned so far and try to handle a full-fledged physical problem. Until then, bye.